Hydrogen is the first element in the periodic table, with the atomic number 1, and it is also the lightest and most abundant element in the universe. Composed of just one proton and one electron, hydrogen is the simplest and most fundamental building block of matter. It plays a central role in the structure of the universe, the function of stars, and the chemistry of life. Despite its simplicity, hydrogen is a remarkably versatile and important element, both in natural processes and in technological applications. In its most common form, hydrogen exists as a diatomic molecule, H2. Under standard conditions, this molecule is a colorless, odorless, tasteless, and highly flammable gas. It has a molecular weight of approximately 2 grams per mole, making it the lightest gas known. This extreme lightness means that when hydrogen is released into the atmosphere, it quickly rises and escapes into space, which is why it is relatively rare in Earth's atmosphere, despite being the most abundant element in the universe. Hydrogen is the primary fuel of stars. In the cores of stars like our Sun, hydrogen atoms undergo a process called nuclear fusion. Through this process, hydrogen nuclei combine under immense pressure and temperature to form helium, releasing an enormous amount of energy in the form of light and heat. This energy sustains the brightness of stars and drives many of the physical processes in the cosmos. The fusion of hydrogen is also the principle behind hydrogen bombs and is a key area of interest in efforts to develop clean, sustainable nuclear fusion energy on Earth. On Earth, hydrogen is most commonly found combined with other elements. Water, for instance, is composed of 2 hydrogen atoms and 1 oxygen atom, H2O. Organic compounds, which are the basis of all known life, also contain hydrogen atoms bonded to carbon and other elements. Hydrogen's ability to form a wide variety of chemical bonds makes it integral to the structure and function of molecules such as proteins, carbohydrates, and DNA. Isotopes of hydrogen add another layer of complexity to this simple element. The most common isotope is protium, which consists of just 1 proton and no neutrons. Deuterium, another isotope, has 1 proton and 1 neutron, and is found in small quantities in water. Water molecules containing deuterium are referred to as heavy water. A third isotope, tritium, has 1 proton and 2 neutrons and is radioactive. While tritium is rare and unstable, it has important applications in scientific research, nuclear weapons, and certain types of luminous devices. In industrial and technological contexts, hydrogen has a wide range of uses. One of the most significant is as a fuel. Hydrogen fuel cells convert chemical energy directly into electricity by combining hydrogen and oxygen, with water as the only byproduct. This technology is being explored as a cleaner alternative to fossil fuels, particularly in transportation, as it produces no greenhouse gases at the point of use. Hydrogen-powered vehicles, including cars, buses, and even trains, are already in use in some parts of the world. Another important industrial application of hydrogen is in the production of ammonia for fertilizers via the Haber-Bosch process. This process involves reacting hydrogen with nitrogen under high pressure and temperature in the presence of a catalyst. The availability of inexpensive hydrogen is crucial to the global agricultural industry, as ammonia is a key component of synthetic fertilizers that sustain crop yields around the world. Hydrogen is also used in the refining of petroleum, in the hydrogenation of fats and oils, in the production of methanol, and in metallurgy for reducing metal ores. In the electronics industry, it's used to create controlled environments during manufacturing processes, and in the chemical industry, it serves as a raw material for various reactions and syntheses. Despite its promise, the use of hydrogen as a widespread energy source still faces several challenges. The production of hydrogen, particularly when derived from fossil fuels like natural gas, can result in significant carbon emissions unless carbon capture technology is used. Producing hydrogen through electrolysis of water using renewable energy, so-called green hydrogen, offers a cleaner solution, but this process is currently more expensive and less efficient than conventional methods. Storage and transport of hydrogen are also problematic due to its low density and high flammability. Compressing or liquefying hydrogen for storage requires significant energy, and special materials are needed to prevent leaks and corrosion. Hydrogen's flammability is, well, both a benefit and a hazard. While it makes hydrogen an effective fuel, it also poses some pretty significant safety risks. Hydrogen ignites easily and, interestingly, burns with an almost invisible flame. Plus, it can leak from containers more easily than other gases because of its small molecular size, which increases the risk of undetected leaks. Historical accidents like the Hindenburg disaster in 1937, when a hydrogen-filled airship caught fire, have really contributed to the perception of hydrogen as a dangerous substance. However, modern technologies and safety standards have, significantly improved the handling and use of hydrogen. Hydrogen also has a role in environmental science and, honestly, in climate change discussions. As a clean-burning fuel that produces only water when combusted or used in fuel cells, hydrogen is being considered as a key component in the transition to a low-carbon economy. Countries around the world are investing in hydrogen strategies to decarbonize sectors that are, well, difficult to electrify, such as heavy industry, aviation, and long-haul transportation. The concept of a hydrogen economy envisions a future where hydrogen replaces fossil fuels in many energy applications, supported by infrastructure for its production, distribution, and storage. So in recent years, hydrogen research has really gained momentum, with advances in catalyst design, electrolysis efficiency, and fuel cell durability. Governments and industries are, collaborating to scale up hydrogen projects and create regulatory frameworks that can support a robust hydrogen market. Pilot projects and hydrogen hubs are starting to emerge in various regions, integrating renewable power, electrolyzers, and transport networks, all in an effort to prove the viability of hydrogen as a central component of sustainable energy systems. In summary, hydrogen is a unique and essential element that touches nearly every aspect of science and technology. From powering the stars to fueling innovative energy solutions on Earth, it represents both the simplicity and the complexity of the natural world. Understanding hydrogen's properties, potential, and challenges is honestly key to harnessing its power for a more sustainable future.